To see how the derivative gets used to answer some application problems, we're going to talk generally about the use of the derivative in algebra and arithmetic, things that we know from high school, to use algebra and arithmetic in order to be able to understand things about the shape of the graph of a function. This will be a benefit to us because in application problems, locating where a graph is on its way up or on its way down or have reached a high point or a low point will have some significance for some various application problems that we'll look at towards the end of chapter 12. So the basic idea is to think about what does the shape of the graph have to do with the derivative. And so in the MyMathLab problems, you'll have some questions like this at the beginning. In fact, there's a lot of questions in this section, but a lot of them are these graphical things. So they don't take very much time to answer. They want to know the intervals on which f prime of x is less than 0. Now remember, f prime of x is slope. And so if you see f prime of x in a problem, you can just rewrite that problem using the word slope. So f prime of x being less than 0 means slope is negative. So it's really asking me where along this curve is the slope negative. And so I have to imagine here, looking at this thing in the direction that the graph is going in. But here the graph is going down, so that's a negative slope. Here the graph is going up, so there's a positive slope here. The graph is going down here, so that's a negative slope, positive slope, positive slope, and positive slope. So the slope being negative or positive tells me whether the graph is on its way down or on its way up. Now if you imagine that this is a graph of, say, the stock market, then you can see why that would be of interest. To know whether something is going down or up on the graph is of interest. So the question here, where is the slope negative? Well, that would be on the interval a to b, and we enter an interval using parentheses. It looks a little bit like a point, so it's hard to, well, it's exactly like a point. So usually when they want you not to read this as an ordered pair as a point, they'll say the interval. And so if they're talking about an interval, then we read this as all the stuff from A to B. Also, the stuff from C to D has a negative slope. And finally, the stuff from E to F has a negative slope. And if we believe all of those things are correct, we would just chain them together with our union symbol, which means or. It means you take the stuff that's between A and B, or between C and D, or between E and F. And we should be able to identify all those intervals. A concise way to express where the derivative is positive and negative is with a sign chart. So for example, if in this previous problem I wanted to make a sign chart for this for the derivative of this graph, it would look something like this. I put f prime up here to remind myself that I'm writing down the stuff I write on this above this line is referring to f prime, and then I can put my letters A, B, C, D, and between A and B I might write a series of negative signs to mean that at any point along the curve between A and B my slope is negative. Between B and C I would write positive signs. Between C and D I would write negative signs. So basically along the graph here, along the number line, next to the f prime, I'm just writing whether the sign of f prime is a plus or a minus. Now at those transition points, at A, at B, at C, at D, it's also useful to label those. For example, at C, the graph has turned over nice and smoothly, and so if we looked very close here, the graph actually would look horizontal at the point C, which means the slope would be 0 there. So I could actually write a 0 here. Again, it's along the f prime, so I'm saying the f prime here is 0, meaning that I have a horizontal tangent line. Most of these other points you don't have a smooth transition. If you circle this point, it does not look like a straight line when you look close enough, and so we would say the derivative there is not defined. So you'll see in the book they'll write ND to mean not defined, and that happens anytime you have one of these sharp corners on the graph. So all of these places where you have a sharp corner, I think there too, it's hard to tell. Anytime you have that sharp transition, you have not defined for the derivative. So across here, when we have transitions from minus to plus along this thing, we should always see a 0 or an ND here. That explains how it transitioned from negative to positive. So that means that if we're given a sign chart for f prime, then we can actually recreate the f, more or less. We can at least recreate the shape. So the trick here is to get used to picturing the sign chart from the picture of f and the picture of f from the sign chart, the more important thing. So my f prime, let me just label A, B, and C here, and D. And this is not going to be a sign chart. Here I'm going to try to draw a graph of f. My slopes are negative until they get to A, where they're 0, which means my graph should be horizontal, and then my graph should have positive slopes. So my graph should have negative slopes, then have a 0 slope, and then start having positive slopes, like that. Now the graph has an undefined slope at B, but it goes from going up, increasing, having positive slopes, to on this side, still having positive slopes. So how is it going to do that? If it has, I mean, one way is it could have a sharp corner there, where it doesn't turn over, but it's a sharp corner. So for example, it could go like that, and then sharply keep going up, so that I have a sharp corner there that does not have a derivative. Or it could be, as we talked about last week, it could be that the function is actually vertical there for a second, and a vertical line also has no slope. Whatever happens also at C, except at C the function stops having a positive slope and starts having a negative slope. So I still have a sharp corner like that, but now my function's coming back down. Then when I get to D, I should have a 0 slope again. This is my slope. But after D, I should start having negative slopes again, so it should continue going down. So even though my slope is 0 here, it should be negative on that side as well. So I have these sharp corners where I have undefined slope. I have horizontal behavior where I have a 0 slope. And then in between, I have negative slopes again, negative slopes, and negative slopes as described in the sign chart. So if I can picture that is what the graph of f looks like, then any questions that I'm asked about the shape of f, I can answer pretty easily. So for example, it asks, does f have a local minimum, maximum, or nothing at x equals a? Well, at x equals a, this is a point where the graph has bottomed out. That's what a local minimum means. A local minimum is a low point on your graph. So there's a local minimum at x equals a. Similarly, there's a local maximum at x equals c. And at x equals b and d, there's nothing. There's no local extreme value. A local extreme value just means a high point or a low point. So c and d are not high points or low points at all. So if I can picture the graph of f from the sign chart, then I can determine where the high points and low points of the graph are. This next problem shows the real power of the calculus that we've learned so far. Everything else we've talked about in the first two problems is just the idea of shape versus slope. But the fact is that we can actually compute algebraically a derivative formula. And so we can create the sign chart using nothing but algebra and arithmetic. So for example, once I find my derivative will use calculus. The derivative of 4 is 0, the derivative of minus 12x is minus 12. The derivative of 6x squared is 12x, and the derivative of x cubed is 3x squared. In order to create the sign chart for f prime, the first thing I need to do is to figure out where are the critical points for the function f. The critical points are places where f prime is 0 or undefined. So if I set my f prime formula equal to 0 and solve for x, I can find the places where the derivative is 0. Notice that f prime here is a polynomial, so there's no square roots, there's no division, so there's no way that I would ever have f prime being undefined. The only way we're going to get undefined in our course is if we try to take square roots of negative numbers or divide by 0. So to solve this polynomial equal to 0, my strategy is always to first factor out any common factor. So in this case, negative 3 goes into every term. So if I factor out the negative 3, I'll have 4 minus 4x plus x squared. And I can factor that polynomial as 2 minus x times 2 minus x. So if that's equal to 0, then that means that one of these values, minus 3, 2 minus x, or 2 minus x, has to be 0. The product being 0 means that one of the pieces is 0. Well, negative 3 is certainly not 0. 2 minus x is 0 when x equals 2, and 2 minus x is 0 when x equals 2. So this is the only value that makes the derivative of f 0. So this will be my only critical value. So down here, I'll write my x values. So at x equals 2, I have a critical value, and that's the only one. So I know that f prime at 2 is 0. So now I'm going to just sample on each side. I'm going to pick a value on each side of 2. So I'll use 0, because that's an easy number to use. I'll use 3 to keep it small. But I get to pick any values I want on either side of the critical values. And for each of those, I'm going to figure out what f prime is. So f prime of 0 and f prime of 3. Because I want to know not what the values are, but I want to know what is the slope. Is it a positive slope or a negative slope at x equals 0 and x equals 3? Well, to get those, you're going to come all the way back to your f prime formula. And if you want to use the factored form of it, that's fine. But you go all the way back to your f prime formula. When we put 0 in here, we get negative 12 plus 0 minus 0. So f prime of 0 is negative 12. F prime of 3, I would get negative 12 plus 36 is 24. Minus 3 times 9, it's minus 27 is negative 3. So on my sign chart for f prime, I will have negative values on this side because I had a negative value for f prime of 0, and I'll have negative values on this side because I had a negative value for f prime of 3. So you can see from this that the graph of f, I'll try to draw a small version of it over here, the graph of f is going to be decreasing, horizontal for a moment, and then decreasing some more. That at x equals 2, at x equals 2, the graph is going to be horizontal, and then it's going to go down some more. So where is the graph increasing? Well, the graph is increasing never. This graph never increases. It's always decreasing. It's decreasing, so I guess we would click here, and there is no solution. For decreasing, we would just use the interval minus infinity to infinity. Some books would like to leave out this point. There's really no reason to do that. But some books would say minus infinity to 2, and then comma also from 2 to infinity. But either answer is correct. I'm not positive which way my math lab does it, but I think it will take either one. They do ask us about if there's a horizontal tangent line, and there is, right there. There's a horizontal tangent line at f, right at x equals 2, but it is not a place where the graph turns over. So we do not have a local extreme value, either a high point or a low point on this graph.